Guys, it's time for a wonderful project today. And that is actually a project that I tried to record already a year ago or so, but then I had to give up just because my C skills were not at that point yet. And I literally didn't have the knowledge to do it. And it's actually quite simple. It's a simple function plotter. So we want to be able to visualize mathematical functions just like in this image here. We want to have an x-axis, a y-axis, and then we want to draw any mathematical function. Now, this is actually a simple graphical tool that we can build in C using STL. That's what we're going to do in this episode. And the difficulty, or the thing that I presumed was difficult, is just the parsing of the expression, because I wanted to be able to, let me just create a new directory, and let's call it plotter. And I want to be able to do something like plot, and then I provide some function like sine x multiplied by 5 plus or minus 4, and that's the function, and I want to plot that. Now, I had no idea how to do it, and now I found a simple way, a super simple way. We won't have to code our own function parser. If you're interested in that, put it in the comments. What we're going to do is we're going to reuse an existing library that's called Tiny Expression, TinyExpr. It's available on GitHub, and this is a tiny recursive descent expression parser. So someone already did the work for us and created this evaluation engine for math expressions. So this is a library that allows us to understand and evaluate these mathematical expressions and retrieve the values, the results from those expressions. And then we just have to combine this library with our skills in creating graphical user interfaces, and then that's already it. So let's just jump right in and create a C file. And we're going to include, of course, SDL2, which we're going to use for our graphical user interface. Now, there are always people in the comments complaining that I should use something more low level, but there's not something more low level. What should I do that's below SDL2? It's like I would have to create some tool that interferes or somehow interacts with X11 or Wayland directly, or something that ties directly into the operating system and writes into video memory. It's horrible. No, really, the lowest level thing you can reasonably do that is cross-platform compliant is SDL2. You cannot, put it in the comments. Let's continue arguing about this topic, but I'm going to continue using SDL. And we're going to use standard IO for printing stuff, and let's create a main method. And that main method is going to, in that main method, we're going to first printf hello plotter. Here we go again. And let's see if that compiles. So let's go into the project's plotter directory here in this pane. And let me see, we have now a new file, plot.c, and I'm going to compile it using all warnings just to avoid unnecessary errors that I can't find, because all warnings will always remind me of everything I can possibly do wrong. And I'm going to create an output file, plot, and the input file is plot.c, and that should be enough for compiling it right now, but that's not going to be the final variant because we're using STL2, so we also have to link the STL2 library, because when we create a window in STL2, let me just show you, STL2 create window. That's the first thing that we're going to do. So we create a window with a title, XY with height and flags. X and Y can be window pause center to center the window on the screen. So let's do that. STL, oh god, again, STL create window, whoops, with a title plotter or math expression plotter. And then XY is STL window pause centered. Same here. And then width and height are hard-coded. Define width is 900 and define height is 600. 900, 600. And the window flags are going to be 0 for now. That creates an STL window as a return value. Let's have a look to confirm it. That's a pointer. So let's just get the window. P window is equal to this. And let's try to compile this. And now I would expect an issue. Yes, right. Because the STL create window is just not defined, we have to properly link the STL libraries. So let's go to STL installation page and copy the flags from here. By the way, let me just show you what those evaluate to. It's just adding some flags that I wouldn't be able to remember. So I always, for years now, no, not years, but for at least 1 year now, since I'm dealing with STL stuff, I'm using these flags and just append them here. I cannot remember them under any circumstances. And people also complain in the comments that I should use a make file, but I find that completely over the top. I mean, I can just append the flags here. I'm not creating huge projects in this on this channel. All right. So what's the warning now? Unused variable. Okay, unused variable is better than undefined reference. Unused variable is just a warning. Undefined reference is an error. Yeah, that's an error, and that's just a warning. Warning is not too bad. Warning is just telling us that something might be wrong, but it's not wrong since we have just coded the single line here of business logic. So we compile, and now we can run the plotter, and as you can see, there was a short pop-up of a graphical user interface, but nothing happened. We have to delay, STL delay, and let's delay for 3 seconds. Compile and plot right away. And that's the window that closes again after 3 seconds. Now we want to keep this window open for a bit longer than 3 seconds, so we have to persist it using an STL event loop. And it's documented somewhere here. That's a very well-known STL pattern, and I'm also explaining it in almost every video, I think. Where is it? Yeah. In STL, we do the following. We poll for events before we, well, that's basically how we interact with the STL window. We listen for, or we poll for events that the STL runtime is giving us. And these events we store in a variable called event. Let's not call it test event. I find test event very weird. Let's just call it event. And then we check if the event.type is equal to STL quit. Then that means that the user pressed the quit button and we can quit the application. And I forgot one more thing. Aside from just polling for events, we need to do another parent loop here that is checking if the app is even running. So if the app is running, or while the app is running, we poll for events. At first, app running is true. And here we do app running is false, and then we should be able to, if the user creates an event and that event is a quit event, then the app running is set to false and the app exits. And this way we can exit the app without weird delays. So let's press the close button and now the graphical user interface closes. Okay, that's working, that's great. By the way, I wonder if, does C have booleans now? Bool? True. I wonder because I learned that C does not have booleans, but this might have changed. Well, does this work now? No. Bool in C. I don't know if C can use booleans. Ah, in standard boolean it's defined. That's interesting. Maybe we'll make use of this in this project as well, just to learn something new. I have never used booleans in C, but if they are defined, well, that's awesome. So let's compile, and that works. And we can close. Okay, that's awesome. Now we can use booleans in C even. Nice. Okay, such a modern language. Wow. Okay. All right. Now, what's the next step? We have a window and we can close it. Now, that's not really getting us very far now. We want to draw to the window. We want to draw to the window surface. So let's get the STL surface from the window. That's the black part of the window. Let me just reopen the window. The black part is what we want to draw to. So that's what we're getting from STL get window surface. There it is from p window. And this should return a p surface. Let me just look up the documentation again. Surface get window surface. There it is. And it just takes as input the window and returns the surface. And on the surface we can draw using STL fill rect. Yeah, we can draw rectangles to the surface. The surface is basically the destination of our graphics, and we can specify rectangles and colors to draw on that surface. I think even in STL, this is the most low-level approach. There are multiple approaches in STL to draw stuff. And usually if you do real game development or something, or some more elaborate graphical user interfaces, you're going to use an STL renderer. But I find this just arbitrarily complicates what we're doing. As long as I can just have some black surface and I paint whatever colors I want onto it, I'm completely fine. I don't need the renderer. I don't need to have any fancy functionality there. I just want to display a simple mathematical function. Keep it as simple as possible at all times, guys. Don't complicate things. Usually, if you complicate things unnecessarily, that's always going to be a performance bottleneck, and it's going to be something you will regret. Except if you properly do something, then that's a different thing. But don't unnecessarily complicate stuff. All right, so here we get the window surface, and then we can create an STL rectangle, and that rectangle is an STL. Let's parse it. I never know if this parsing, if this casting is necessary. An STL rectangle consists of, same as the window here, of an X and Y coordinate and a width and a height. So let's just set all of those to 50. And then the color is, let's say, red. This is an RGB color, so RGB, red is set to 255 in decimal, and the others are 0. That should be red. And then we can do STL fill rectangle on P surface. we provide the address of the rectangle and the color. And then while the app is running, we update the screen. Because right now, if we compile this now, let's see. Oh, it doesn't work. There's an error. I called SDL fill rects. That's wrong. I need to call SDL fill rect because I'm just creating a single rectangle. Oh, and one more issue. The color should be a uint32 because there are multiple size data types. There's also uint8 and uint16, for example. And now you can see that the display here, the surface is still black. Black is not good. We want a colorful rectangle on the surface. So what we need to do is we need to tell SDL that we have drawn something onto it. So let's do SDL update Windows surface. Not Windows surface recs. We want to update the entire surface. And we pass the window as input to tell the window to update its surface. Let's go. And there's our red rectangle. Now, that's essentially it. That's basically the graphics part. If we now want to draw a mathematical function, then we need to, well, right now we have drawn a rectangle here. And now we should draw maybe a centered XY axis. Yeah, let's do that. So let's create a new function. Draw grid. Let's draw the grid onto P window or onto P surface. We draw the grid onto the surface. So void draw grid SDL surface pointer P surface. And then what we need to do is we need to decide on how to position the grid. What is our 0 coordinate? And I would say our 0 coordinate should be in the center of the screen. All right, so we have the display coordinate starting in the top left corner, which we use for graphical representation. For example, for displaying this rectangle, we had to specify we want to offset the rectangle at 50-50, at x50 and y50, so it's displayed here. But if we want to display the mathematical functions in the center of the screen, then we need to redefine this offset for our drawing and say that 0, 0 is the center of the screen. So actually what we can do is before we even draw the grid, we can define a new drawing function that draws something at corrected coordinates. At our mathematical grid coordinates. Let's do that maybe. Draw and instead of at the display coordinates, I want to draw at grid coordinate. So I want to draw to the SDL surface as always, P surface. And then I want to draw, what do I want to draw on the surface? I want to draw an SDL rectangle with a specific color. Maybe this should be a pointer as well. And a color, uint32 color. So how do we draw something at the grid coordinate? We define the grid coordinate as int xgrid is equal to, then the offset is now always measured as relative to the center of the screen. So we do width divided by 2, that's the center, plus p rect x. So, or instead of creating a new variable, xgrid, we can just update the rectangle. We can just, no, we shouldn't update the rectangle in memory, because we just want to draw this rectangle in memory. So we could do this a bit inefficiently by reallocating new variables here. Yeah, it's not entirely ideal from a performance standpoint, but I find this quite clear. And we're coding such a simple application. I mean, this is probably going to be fine. So this is now our x and y coordinate, and for y we should maybe even invert the direction of y, because from a display standpoint y is an offset pointing down, because that's how the rectangle was originally drawn. We specified y as 50, and then it shifted the rectangle down by 50 pixels. Now in mathematical functions, y is usually pointing up. So we need to invert the direction of y, I think. So whatever the offset of the rectangle in y is, for example, if it's 50 again, then we want it to be 50 above the center line of the screen. So we should do minus p rect y. Okay, I'm really excited to see if this works. And now the next thing to do is draw at grid coordinate. The next thing to do is we should draw, SDL fill rectangle, and we draw something to the surface. We draw a shifted rectangle to the surface, shifted rect, with the same color, of course. And the shifted rectangle is a new rectangle, so let's allocate one. SDL rect shifted rectangle is equal to, and it's essentially the same rectangle as the one we are given. So let's get, except for the x and y coordinates, of course. So x and y are the new coordinates which we have calculated above. X grid, y grid, and then we can take from p rect the width and height. I think it's just w and y. And this is now our shifted rectangle, and it's filled here. So now if we, instead of filling the rectangle here, we can draw at grid coordinate on the surface our rectangle. With a specific color, and let's see if this works. Yeah, now, as you can see, the rectangle is not positioned in the top left corner. It's now positioned at roughly the center of the screen, but offset 50-50, x50 and y50. And that's exactly what we wanted. I'm just wondering how the width and height represent in the new coordinates. But that is not important, actually. Not very important, because the width and height are not important, because we're just going to display thin lines in our plotter. So we don't even need to worry about display and height, about the width and height too much, because essentially our rectangles will be single pixels or maybe 2 or 3 pixels wide. So I'd say this is good. So we now can draw rectangles at grid coordinates. Now we can draw the grid. The grid is essentially, we essentially need to now draw rectangles at the center coordinate. Yeah, let's see. We're going to draw we're going to create a rectangle. Pixel. Or no. We're going to loop over the x-coordinate. The x-coordinate starts at 0. No, it starts at minus width divided by 2 because we want to start at the left side of the screen. And we're going to use the grid coordinates as a representation here. That's why we start not at 0, but at minus width divided by 2. While x is bigger than width divided by 2, x plus plus. And we're going to draw at grid coordinate on the P surface a rectangle. Maybe let's try to create a rectangle here. Or let's call it pixel or axis pixel. And that axis pixel is an STL rectangle with the specification x. Well, it doesn't matter at first. Y doesn't matter at first. Well, actually, they don't matter at all, those properties, because we set them here. So let's set them here. The only thing that matters about axis pixel is that the width is equal to, let's say 2, and the height is 2 as well. And then we set axis pixel dot width dot x equal to x. And y, what's the y coordinate for the x line? It's 0, of course. And then we draw at grid coordinates the axis pixel, and the color is just white. And something doesn't work. There's an error. Of course, I need to declare the variable data, the data type of x. Oops. It's an integer. Alrighty. And there's no axis, and that's because I forgot calling draw grid here. And there's still nothing. And that might be because I'm essentially maybe I need to create a new rectangle for all of those. Wait, this is actually a stupid way to do it. This could be a very simple rectangle. This could be a single rectangle. Wait. The grid could be so much simpler. Why didn't anybody tell me that before? I think I did this method more often. Let's do the following. No. We create an STL rectangle that is the x-axis, the complete x-axis, and the x-axis dot width is equal to, no, the x-coordinate is equal to width divided by 2 minus width divided by 2. The y the y coordinate is equal to 0. And the width, and now that's the important part, the width is equal to width. I don't need a loop. I can just create a single rectangle that has the entire width of the screen. And the height is equal to, let's say, 2 pixels. And then we can draw that rectangle at grid coordinates. Okay, let's see what happens now. Of course, the height field is not defined. It's h. And now it's still not drawing. I have no idea why it's not drawing. Let's have a look at the warnings. The warnings usually give the answer. In function, draw grid. Implicit declaration of function, draw at grid coordinate. That's the answer. Draw at grid coordinate is, of course, used by draw grid, so we have to place it above draw grid. Let's see. Nope, this is still not it. In function draw. And there's no warning right now. So what's the issue here? What's even the color that I'm using? It's draw at grid coordinates. Draw grid. The grid is this. Why is this? What? Maybe. Wait, if I just change the y value. Oh, there's something now. That's definitely wrong, but it's something. What if I change this to 20? What? What's that? X-axis, y coordinate. The x-axis, x coordinate is this. The y coordinate is this. This is now actually exactly the line that I want to have, but why is the y coordinate now? Why does it have to be 2? I mean, it should be, wait, shouldn't it be 0? Yeah, it should be 0. And then from that y coordinate, the height should create a height of 2. Or am I somehow stupid? I'm probably messing up something here. The SDR rectangle. Let's have a look at the SDR rect definition. It's xy width height. And I specify here xy width y. That's it. Okay. So that's the height. And now we have our x-axis line. That's good. Now we can do the other line as well. It's effectively the same thing. Let's just replace the string x with, let's replace x with y. That's now a failed replacement. It replaced axis with a with. So axis. Oh god, this is so stupid. Let's improve this replacement. Wait, let's highlight it all, substitute x underscore with y underscore. That should work better. Okay. So the x coordinate is now 0. The y coordinate is now starting at height divided by 2, at minus height divided by 2. The width is 2 and the height is height. And this doesn't work because x is 0. Y is minus height divided by 2. Width is 2. Height is height. What if I change the x value? No, still nothing. Y-axis x is 0. That's correct, because the y-axis always is positioned at x equals 0. The y-axis y coordinate starts at height. No, it starts at height divided by 2. Because I have to remember that the top of the screen is now positive y. I was thinking in display coordinates where the top of the screen is 0y or negative y, where up is negative y movement. That's what I was thinking. And now we have a proper grid. That's great. We can improve the looks a bit by defining a gray color. For example, 050505. And let's replace the grid colors with this gray color. Draw at grid, gray. By the way, is it gray with A or gray with E? Gray or gray? Can never remember that. Gray is American English, whereas gray with E is more common in British English. Okay, fine. I don't care then. Oh, that's very dark. I have to make it a bit dark, a bit lighter. So let's pick 101010. And we're defining a gray because I don't want the lines to pop out on the screen so much. I want the actual function to be the interesting part of the screen. 141414 maybe. This looks okay-ish, maybe just one bit brighter. Let's make it a hint more brighter. 333. That's good. Okay, that's very good. Okay. Now, what we want to do is we want to draw a function. Now comes the interesting part. Actually, now we prepared everything, or almost everything. The only thing that still stands out to me is how this rectangle is positioned. Because it's offset at x by 50 pixels, that's correct. And it's offset at y by 50 pixels. But then width and height still seem to draw down and right. Yeah, but as I said, if the rectangle is, well, we're going to use the rectangle only for plotting the function, which is a thin line, so the movement down, the expansion down and right doesn't really matter at all. Of course, if you want to allow very thick plotting, for whatever reason you want lines with a width of 20 pixels or so, then you have to center the rectangle somehow. So if we draw at grid coordinate, well, or maybe we can try to center it. The X grid and Y grid is this. The rectangle width and height is this. Maybe the width has to... So the starting X has to be offset by P rect width divided by 2, and same for Y, minus P or plus. Maybe plus, because here the direction is inverted. H divided by 2. Okay, and I think now we should have a rectangle that is what the hell? We should have a rectangle that is centered at the new coordinate. What's wrong now? P rect X minus P rect W divided by 2 and P rect H divided by 2. It's now offset by 50x, and that's something is wrong here. What, did I delete anything weird? No. Is anything weird happening down here? Draw at grid coordinates the rectangle. Let's draw it at 100 and 100. Ah, no. 100 and 100. Where did the lines now go? I didn't even modify the lines, did I? Ah, it's a division by 0. No, it's not. I definitely reused this method to draw the lines here, and that might cause problems. No, let's forget the centering of the rectangles. Ah, I think I know why. If we divide the width and the height by 2 here, yeah, well, what we're seeing on the screen is definitely that we have lines that are divided by 2. So you see half of the line being drawn and the other half is not drawn. And that's definitely a side effect of this change. Now let's forget about this centering. It's completely unimportant for this project. Let's keep things as simple as possible to achieve our final goal. We shouldn't overcomplicate stuff. We could, but we won't. All right, let's deal with the tiny expression to parse mathematic functions. So what it's doing is it's a parser for math expressions. It can be installed very simply, apparently. It's self-contained within 2 files, tiny expression C and tiny expression H. So we have to just download those 2 files. Where are they? View all files, and there they are, tiny expression C and tiny expression.h. So all of this is the library source code. Let's go to raw and copy the link, and in our projects directory, let's do this to download the file. There it is. Let's check if it's correct, and this looks like the proper source code. Great, and let's do the same thing for the other file, for the header file. No, wait, which file did I download? The C file. Again, .h is here, raw file, link, copy, wget, and there it is. And this looks like a header. Okay, and the interesting part about tiny expression is that it has only 4 functions that we as the user need to use. Let's have a look at the GitHub short example. Well, even if we used the interpret function, that can be used without any overhead. It's to evaluate expressions directly, but these can't have any variables. So this is useful for evaluating simple calculations as in a calculator. So here you can do 10 plus 5, 5 multiplied by 5, 3 divided by 5, whatever. If we want to use variables, which would be important in a plotter, then we have to use the compile. We have to compile an expression. We have to evaluate it and then free it. And the compiled expression is basically a string with the expression. That is what the user can input. Then we provide variables, in our case x, and a count, the variable count, and some error return code. This returns an expression, and then we can evaluate this expression in a separate call, which gives us a double result, and then we can free the expression. So it should be quite simple, no? And since our plotter, is just a simple two-dimensional plotter, the expression will only have one variable. It will be x, and that will compute a y value, and that's essentially it, I think. So let's have a look. So how do we compile an expression? We do the following. There's an example here. We first declare the variable names and pointers. Let's just copy this. Let's copy this and then modify it to our needs. As I said, we are only going to use a single variable. Now, this looks like I'm mixing up responsibilities of the main function again. So here I'm drawing all the STL stuff and creating the the loop. Yeah, I know it's not ideal. Let's delete the rectangle. The grid is drawn here. Draw at grid coordinate rectangle can be deleted. Now we should only have a grid, right? And now we want to get the user's input int argc int and then character pointer argv. And we expect from the user, what input should a plotter expect? Let's check it. So the usage is the following: printf usage. The first argument is the negative x coordinate, right? No, but that would even more complicate our drawing to the screen. No, we can keep it super simple by doing, I wanted to define a negative x and y range, an x range and a y range, but that might be over the top, because then we have to perform scaling and stuff like that. No, let's keep it more simple. Let's just take as user input an expression for now. Yeah, that's the simplest thing that we can do right now. So we take as input an expression. Let's not annoy the user with having to specify the x and y ranges and the step size and things like that. So the argument count that is expected is therefore 2. First of all, the program name, argv0, and the first provided argument, the expression. If it's not 2, then we return this. All right. Then we create an STL window right here. actually, we don't even need to update the window surface all the time. We just need to update it once because we're not doing any dynamic live animations in this project. Then we draw the grid, and after we draw the grid, we want to draw the function. So draw expression. And this takes as input the user's expression. Or we could allocate a constant character, or maybe a character pointer expression, and that is equal to argv1. So here we draw the expression, and then up here we create a new function, void draw expression. And of course we need to draw to the surface again. So let's take the SDL surface as an input, p surface, and then we have to get the expression as another input. That's fine. Then down here, let's add the p surface again, surface expression. And up here, now the magic begins. Minute 51 of the video, the magic begins now. Well, okay, the part before that was also magical, but now the real magic begins, the interesting part. We have to include the library that we want to use. So let's include this as the most important library as a first thing. Let's put it in quotes because we know it's located in the same folder as our source code, tiny expression.h. And now we can use functions from tiny expression. Let's have a look. We want to define variables. In our case, we just need a single variable. And that is double x. Yeah, because that's the variable part of the expression. Store variable names and pointers. We just need x, so let's remove the y part. Okay. And this seems to be a nested structure here. A structure that contains another structure that contains a string and a pointer to a double, if I understand it correctly. Then we allocate an error code. Then we compile the expression. So let's compile the we compile the expression. We give it the user's input, the variables. What's the number 2? That's the count of variables that we have, and then the error. So let's do te compile. Te compile, and now Vim also auto completes those because they are located in the same directory and properly linked up or included up here. Te compile, we compile the expression, variables, count is 1 in our case, and the error code is this, and we pass this as a pointer, if I recall correctly. Yes. Now we have to check if the expression is not null. Then we get the result by evaluating it. Oh, and here we even set the input x value. Okay, that's interesting. So if the x, wait, we have to store the expression. Te expression is here. Te expression pointer p expression. is equal to this. If the p expression pointer is evaluated, then something will happen, else we print f to we do an fprint f to standard error, and we say error evaluating expression, and then we print the expression that we were given here, expression. And then we terminate the application by doing exit. And this can be, an exit comes from standard lib. Okay. Let's try to now compile our software, and now it will say missing initializer for field type of TE variable. What? Missing initializer for field type of TE variable. So there's a new field in TE variable that is not documented. Or maybe we cannot. No, what's the issue? I'm completely messing up something here. We have to compile. This will return an expression. No, I'm not messing it up. Then TE variables. That's an array. No, that's correct. Let's have a look at tinyexpression.h and have a look at how TE variable is defined. So a variable can have a name, an address, a type, and a context. But then how the hell does this initialize the variables? Name, address, type, context. Name, address. That's the name. That's the address. What's the warning again? Missing initializer for field type. Why is this not allowed? Do I have to initialize all of the fields myself? What is type? It's not documented anywhere what the type is and what the context is. I don't even know if I have to really allocate this myself. Is this just a warning? Yes, it's just a warning. So maybe it's fine. It's just warning us that we haven't initialized all of the fields. But then there's an error here. Undefined reference to TE compile. That's the real issue. And why? What's the issue here? It's defined here. We provide an expression, variables, variable count, and error. expression variables. Maybe we need to pass the variables as a pointer. Yes, okay. And the expression here is already a pointer. Okay, I think we're good to go. Undefined reference to TE compile. Constant TE variables. Expected constant TE variable pointer, but argument is of type TE variable pointer. No, wait, but variables is already a pointer because it's an array. So it should work. Undefined reference to TE compile. What am I messing up here? TE expression, pointer expression, TE compile, this. No. I feel a bit stupid right now. Undefined reference. Why is this an undefined reference? It's defined right. It's defined right here. Parses the input expression and binds variables. TE expression, pointer TE compile, constant character pointer expression, constant TE variable, variable pointer, variable count, int error. That's TE compile. What am I calling? TE compile. And what's the warning? Undefined reference to TE compile. That's the first method that we are using. So maybe I'm just not properly telling the compiler that I want to use tinyexpression.h and that the source code resides in the same directory. But then I think it should also already complain at TE variable. No, but TE variable is already completely fully defined in the header, which is linked. I think this is a very, very basic C linking issue. So what does the library say? Include tinyexpression.h. To use tinyexpression, simply add those two files to your project. C add single header library. GCC header search path, or GCC, wait, I really don't get why it doesn't work. I mean, it's all located in the same directory. C multiple C files. If you have your two source files, you can compile them into object files without linking us. So and then you can link them all. Okay. Let's try again. I'm compiling output plot C, but I also want to compile tiny expression.c. Does that work? Where did my plot file even go? Huh. So now what's the issue? Error adding symbols, DSO missing from command line. You should define the functions that you want to call from modules.c into main.c into a header file and include that header file in main.c. Yeah, I've done that. Once you have the header file, please compile both of the files together. Yeah, I'm doing that. Am I not? DSO missing. This is using libmath, so it's also missing me linking the math library, so I have to attach -lm here. Oh, and now it works. It works, guys. It works. Okay, so I just had to figure out how to properly compile it. I have never really done a big multi-file project, as you can tell. So, usage plot expression. Now let's fix the usage printout and attach a new line here. And now it works. Okay, so we get the warnings from the compiler, that's fine, and then we get a usage printout. Of course, the warnings from the compiler only stem from the fact that I compile and I execute right away, just to save some time. But if I execute only the plot executable, then it will of course only print the usage. Now we plot and we specify our own expression. So let's do something like sin x. And it seems to work, at least in the sense that we don't get an error. Okay, and let's specify an invalid expression like sin x without a closed parenthesis, and that caused an error evaluating expression. That's very good. So it seems to be quite robust already. Now, here we store variable names and pointers, then we compile the expression, and then we want to evaluate the expression. How do we evaluate the expression? We do t-eval. Okay. T-eval. T-eval, okay. Evaluate expression, and then we pass an expression, p expression, and of course now it will evaluate the expression and return a result. Yes, let's check the result. Double result is equal to this, and then we can also print the result, printf results is equal to this. This is just a temporary printout of the result, and it should print 0 in my opinion, because sin of 0, because we haven't set the value of x, and it should default to 0 if I'm not mistaken, should print 0. It doesn't print anything. Maybe because x contains weird stuff. If we set x to 0 explicitly, I mean, we cannot guarantee the content of something if we don't set it. No. No. We have to first compile, of course. So we compile this, and then we call plot of sin x. Result is 0. Okay, that's fine. That's exactly what I expected. Let's try of 1. And let's see if that... it still prints 0 because I'm printing a full integer here instead of a floating point number. So let's print a floating point number. Oh, and I'm super stupid because I haven't even passed a variable here. Oh god. Yeah. Again, let's... Okay, and here the result is 1. That's definitely wrong. Ah, because I have to print the result and not x. Okay, let's try again. Sorry for those super stupid mistakes. Now this looks correct. Okay, so we are able to evaluate any mathematic function, guys. Let's do -5 and then multiplied by x squared. And we have a result. That's awesome. That's super powerful, by the way. That's super powerful. We can now evaluate any mathematic function. Okay, and now instead of evaluating just a single mathematic function at a single value, we need to evaluate it at all the values. Yeah, we need to evaluate it at all the values. So let's define. We still have to do some scaling, but let's not ask the user to do this. So x range, let's say, or x starting coordinate is -10, and x end is +10. And of course we do the same thing for y. Y start, oh god, y start is -10 and let's say -5, and y end is +5. That's basically the range which we want to plot. And now here we start setting x as x start. This is the starting value at which we want to start evaluating x. And then here we print. Now we loop over all the steps. So step or int I equals 0, or no. For x equals x start, x equals x start at first, then x while x is smaller than x end. Yeah. X plus equals the step size, x step. Let's create a step size, or let's just call it only step, and the step size is I don't know, 0.1. Okay. So we loop over the x range, we calculate results. The result is of course the y value, so let's just call it y. And then let's print the results. Or let's draw the results. And we draw the results by drawing at grid coordinate. And now actually we should have another function on top of draw grid coordinate. No, or we should refine the grid coordinate function. Because now we have to scale the display even more. Now let's keep the draw at grid coordinate and let's do double y equals this. And then we draw at grid coordinate. What do we draw there? Surface rectangle color. P surface rectangle. Let's call it xy. Oh no, let's call it rectangle. And the color is 0x, ff. Basically, it's white. The rectangle is an SDL rectangle that's reflecting the individual points of the line. SDL rect. The x value is x, the y value is y, of course, and the width and height are, let's say, 2. We want a line that has a width and height of 2. Or rather, a diameter of something around the value of 2 to be precise. And that's the rectangle, and then we want to draw at the grid coordinate this rectangle. Now we should already be able to draw something, but the coordinate system will be off. The coordinate system will be off. Let's just have a look at the result. Let's have a look at the simple function, sin x. Nothing is drawn. Y. For x start. Of course, because I didn't compile. That's why, by the way, I always like to just compile and execute in one go, because I always forget compiling. So let's do this again. So here x step must be replaced with step. Step. And of course, the rectangle here must be a pointer. And this is our plot, guys. So it's plotting something starting from x start to x end. But of course, now the display coordinates are still, or the grid coordinates are still ranging from, they are still in pixel values. That's why the actual plot is so much smaller. So we have to scale this a bit. So we want to draw something at the grid coordinate. How do we draw something at the grid coordinate? We draw x grid equals width divided by 2. Width divided by 2. And then we need to scale all of this. How do we scale it? Maybe width divided by 2. No. I wanted to somehow divide it by the scale factor. Actually, one hacky way would be, instead of transforming the coordinates here, we could transform the actual expression that the user provides by scaling it with a factor. But no, that would be stupid. So the scale factor is this x scale is equal to x start divided by x end. I hope this works. I don't know if these expressions work. And same for y scale. So what we do is here draw at grid coordinate, we expect the user to input some rectangle at the convenient grid coordinates that they would expect, defined by those limits and scales. And then we need this function to transform the input into actual pixel values. So actually that is not xgrid, it's xDisplay. This is the display coordinate. And the given grid coordinate is actually this one right here. And I think we have to scale this by x scale. And we have to scale y by y scale. I think I'm just going to try it. I have a hard time imagining those things. X display and Y display. And now I really hope that the grid drawing still works, because now the grid drawing doesn't draw the x-axis at minus width divided by 2. It starts at minus x, at x start, and finishes at x end. X end, y is 0, that's correct. And then same thing here. Y start, y end. Okay, let's see. Something doesn't work. Y disp doesn't work, it's undeclared. Int y display. Missing, no. Error y disp undeclared. First use in this function, did you mean x disp? I forgot a semicolon, that's why. End is undeclared. Where do I use just end? Here. X start divided by x end, of course. And this must be y end then. Let's see. Okay. It's getting worse. I think we can have a look at this in a debugger. Wait, what we're doing is we are calculating the display thing in this way. Rect multiplied x scale. What is x scale? X scale is x start. That doesn't make any sense. It's actually the width of the screen divided by x start minus x end, or rather x end minus x start. Because if x end minus x start is as long as the entire screen, then the scale will be 1. If x end minus x start is something smaller, for example, if we just want a range from -10 to 10, then this will result in something big, and this will be the new x scale value. Yeah, I think that's it. Same for this. We have to do y end minus y start. Okay, let's see. This doesn't look too bad. At least we now fill the screen. And x starts at x. The x-axis starts at start, that's fine. And it ends at end, that's fine. Let's have another look at this. Yeah, something is definitely wrong. What if I set the step size to 0.01? Does this change the output? Just to see what the effect is. No, it doesn't. Okay, y scale is this. Okay, let's first fix the grid drawing. Let's do this systematically. We fix the grid drawing. How's the grid drawn? The grid is drawn by taking the, well, by first saying that x starts at x start, which makes sense. Then the axis y is 0, then the x end is, then the width is x end, and the height is 2. That makes sense. Then we draw this at grid coordinates. And one more thing that we might have to do is we have to, in this case, also scale the width and the height. What if we do this? X scale, Y scale. Okay, now it's definitely scaled. Actually, we don't want to scale the width and the height because I don't want the axis width and height going bigger. So, but at least now it's continuous. Width, X scale, wide, height scale. So let's keep it at 2 pixels. Then we draw a X display. That X display is width divided by 2 plus the X coordinate multiplied by X scale. Same for Y. Height divided by 2 minus p rect multiplied by Y scale. Oh, wait. No, here. No. Wait, one weird thing is that the rectangle that we want to draw here starts at x start, and here this x start is scaled. So if we scale x start, which is -10, with x scaled, what is the result? Its width is 900 divided by x end minus x start. X end minus x start is 20. So the result, the scale is 45. And then we do -10 multiplied by 45, which is correct. It's -450. And then we offset by width divided by 2, which is 0 again. So this should be 0. Yeah, that's correct. So actually, I think it should make sense. The width should be... Yeah, the width should be scaled, of course. Multiplied by x scale. The height should be multiplied by y scale. But then, that's somehow a stupid way to draw, because then that doesn't just scale what we... It also scales... oh no. No, I want to do only single. No. Let's do it differently. Draw at grid coordinate takes as input only rectangles, and rectangles are only single pixels. Let's just say we only want to draw single pixels or small rectangles that don't scale. We don't increase or decrease the size of individual rectangles. Yeah, so we retain the width and height. That means we have to draw the grid coordinates by looping over the x-axis, and we are not going to use this width and height thing, because here we are creating a rectangle with a big width that doesn't make sense if we want to scale it. So we do something like int y equals 0, y starts at... No, y is always 0 for x. X equals x start, x smaller than x end, x is incremented by, and let's say x is a double in case there are floating point operations, and then we increment it by something very small. Something super small. Let's say we take the step size and make it even smaller, just to make sure that the grid is always drawn properly. So we place many pixels. This is definitely not the best, most efficient way to do it, but I'm going to do it to finally get a working system. All right. So we're drawing something. We're drawing x-axis rectangles. Let's pull this in here. X-axis, and the x-axis dot x is equal to x axis y. Oh, let's do it all here. STL rect x is equal to x, y is equal to 0, and the width and the height are going to be 2. And up here, I define a new constant, define a thickness constant, and that's going to be 2. All right. And this is going to be set here, thickness. Okay. And then we draw at grid coordinates. Let's see what happens now. Error y is not defined, of course, because it's 0. Okay, it still looks like it's not working. Then we do the same thing for y. Well, let's just ignore y for a second and print now. Why is it still printing the same thing? I don't care. Let's do the same for y. So for double y equals y start, y is smaller than y end, y plus equals step divided by 100. And then the y-axis pixels, y-axis pixels are placed at x0, y, with a specific thickness, and we draw at grid coordinate the y-axis here. Okay, very good. So now we have an x and a y axis, apparently. They are just not drawn very well, but we can see something. So we have to, how do we increment x in order to set small rectangles that touch each other? That's a good question. Actually, just setting a very small step size should be fine. I mean, why wouldn't this work? What if I do something like 00001? Somehow this doesn't work. Or it does work, but I don't see it. What if I do the same for y? Ah, I get it. It's probably some integer double conversion issue. Here we are calculating something, and this must all be a double value, I think. So the integer x displaced is this. Then we get the x coordinate of something, and if this is a very small value, yeah, we should convert it to a double, multiply it with the scale. Let's also make this a double just to make sure. Let's see. No change so far. Double. still looks trashy. But why? We draw a grid here. We have doubles. The rectangle. The rectangle of course doesn't the rectangle is messing with our data. No, we shouldn't misuse the rectangle here. We should accept double x and double y. And then we should draw at our own means without using the rectangle as a transport object. So let's draw at grid coordinate x 0 gray, and let's do the same thing down here, 0 y gray. Then in here, instead of using the rectangle x, let's use x, and instead of using rectangle y, let's use y, and this computes the display pixels effectively. And let's see, something doesn't work, of course. Too few arguments. I need to update this call down here. No, I need to update draw at this. I need to update this down here. Right. So I want to draw mathematical results at x, y with the specific color. Okay, let's go. Why is nothing happening? Prect is undeclared. Where, what? Prect? Of course, the width and the height are now thickness, which are globally declared. And now, oh guys, it's working. Awesome. It seems to be working, and it's even working at scale. And it's crazy. Okay, it's quite slow because I have an incredibly small step size here. So let's fix that up. So let's make this the step size. And this, I don't know if this will work and if this will look good. Still looks good and is much faster. Okay, so that works. Now we can even let the user input x start, x end, y start, and y end, and the step size. Yeah, let's do that. So for that, we need to have global variables. It's the simplest way to just forward data. So let's create double x start is equal to -10. X end is equal to 10. Then y start is equal to 5. And then y end is equal to y start must be equal to -5, y end must be equal to 5. And now the step size is equal to 0.01. And I think in draw grid we shouldn't make this dependent on the user's input step size, actually. No, okay, let's just keep it for now. And then yeah. Okay, x scale. Where's x scale used? It's used here. So the x scale is now I'm just wondering, should this be a function double get scale for a double end, for a double start and end? Yeah, I think it, yeah, double end. And this returns the width divided by x end minus x start. Let's just cast the width to double just to be sure. But that's just for the x scale. Because for the y scale, we need to use the height here. Okay, and then we can delete all of those and ask the user to input not just the expression, but x start, x end, y start, y end, and step size. So now we have quite a bunch of arguments, but now we can do everything. X start, X end, so that's 1, 2, 3, 4, 5, 6, 7. 7 arguments. Okay. So if we have 7 arguments, then we can set the global variables to their values. X start is equal to arg v1. The expression is now equal to this value. Then y start is equal to arg v2. Don't forget the semicolons. Then the end variables are those, and the step size is this one. Okay, and then we have the expression here. All right, and now we need to replace the usages of the start some. Yeah, we need to replace the usages of the constants that we had defined before. So x start would be get x. X scale would be get x scale for x start and x end. I know it's not super fast to compute it all the time, but let's just keep it. Okay, we don't need to cast to double anymore. We also don't need the parentheses anymore. Now, what's left? X start and X end are X start and X end lowercase. They are just global variables. Y start is this. Y end is this. And the step size is step. X start. Actually, I should have done a global replace, but I think I have them all now. X start. Yeah. Okay. And I think if everything works, let's see. No, it doesn't work. Why? Incompatible types when assigning to type double from character. Oh, of course. For converting the input arguments, we will use A to D. Does it? No, it does not exist. There's A to I, A to L, A to... we have to accept integer arguments. So let's just accept integer arguments for now. For setting the boundaries, the boundary box of the plot. Yeah. So we do A to I, that converts the input string to an input integer. Oops. A to I. Yeah, and the expression, of course, is still a string. And now let's try and see. Of course, it's giving me a warning now here that I have to specify x start, x end, y start, y end, and the step size. So let's do that. Plot x start is let's say -5 or minus 12. X end is +12. Y start is -6, and y end is +6. Step size is this. Oh, but this cannot be an integer. Man, A to I for double. A to F, convert a character string to double. Man, A to F. Okay. This is what I was looking for. Oh, then let's replace all the A to I's to A to F's. Cannot harm. A to F. ATOF. All right. And let's try again to plot from -12 to +12, -6 to +6. And step size is this. And the expression is, let's say, sine x multiplied by x squared. And this doesn't work. There was an error. Syntax error near unexpected token. I of course have to recompile. And now I can try this. So if this works, this is crazy. This is a super powerful application actually that we just coded in under 2 hours. So we can now plot any function, if this works, from any x range to within any x range, within any y range, and any step size or any accuracy. And we can specify any function that we parse and evaluate. So let's try to execute this. Syntax error. Crazy. Compile. Maybe the bash evaluation is not handling those special characters well, so I have to put this in quotes. And something is not working. Why? Do I have to put all of those in quotes maybe? Just to be sure that bash does not do some weird things with it? No. I need to jump in a debugger and check out what it's doing. Plot. Layout. Source. Wait. No, I need to compile with dash G. Yeah, I'm doing that. Okay. Layout source. Let's put a breakpoint in line 89. Or even in line 91. There it is. Let's run with the arguments -12 to 12, -6 to 6. Step size is 0.001. And then the expression is sine x. Let's just keep sine x to keep it simple. Now, we can print the step size here. That's properly input. Let's print the expression. It's also properly done. Let's print y end, print y start. Yeah, I've got it. The issue is that y start should be the third argument, not the second one. The second one is x end. So now the input arguments were mixed up. Okay, let's see. Does this work now? No, because I haven't compiled. And there we go. It's working, guys. Of course, no, it's not working. Something is wrong. The scale of the y-axis is somehow broken. Of course. Yeah. It's because I need to check y end and y start. You probably all saw this and thought, hey, when is he going to fix that one? All right, and now if I compile now and execute now, so then we should plot from -12 to 12 x and -6 to 10 y and step size 0.001, the function sine x multiplied by x squared. Something is still wrong here. So somewhere something is wrong. We just have to find out where. X start, X end step looks correct. XY looks correct. Variable is X looks correct. Up here, X start, X end looks correct, right? Y start, Y end looks correct. I think I know what's going on. The issue is that currently we are scaling. The input is currently that y should range from -6 to 10. However, currently the application only supports zero-centered scaling. Because here in the draw at grid coordinate, we just offset by the height and then scale y, but there's no y center scaling. So we could do -y multiplied by get y scale, but y should be scaled as well by the center value of y, and that is y start minus y end, I think. Y minus y start minus y end, normally, or even plus y end. No, y end. No. Something is wrong here. So we currently allow only scaling around the center. We need to offset it as well a bit. Y multiplied by get y scale. Minus, and what's the offset of the y-axis? Minus y multiplied by, no. Y end minus y start multiplied by get. I'm almost guessing now. Something like this we need, but I don't know if it's quite correct. Of course I need to compile. Yeah, no, this is completely wrong. Y end minus y start. What's the center of y? We need to... it's y end minus y start. Divided by something. Y end minus y start. In this case, the center is 0. How do we know that? How do we calculate that? We need to calculate y end minus y start. No. X multiplied by x get scale. Y multiplied by y get y scale. Yeah, the offset is tricky. Get x scale. X multiplied by get x scale. We need to do... This is so simple, guys. I just can't wrap my head around these geometric transformations. Why? So this is centering the coordinates. This is subtracting y multiplied by the scale. But if the range of y is not located at the center of the screen, then we need to do something else. For example, if y ranges from, let's say, 0 to 10, then the x-axis must be located at the bottom of the screen. How do we do that? Plus It must be something like this, but this multiplier is definitely wrong. Let's just have a look. Yeah. Wait, what about minus? Oh, no, I need to compile. Yeah, it's completely wrong. Get Y scale. This was the fix. This is the fix, guys. Somehow I just had some thoughts and they told me that I have to use y multiplied by get y scale. No. This cannot be the fix. This cannot be the fix, guys. Because I'm already doing minus y get y scale here. Y, maybe y minus y start. Something like this. We need something like this. But this looks quite correct. But this is not correct. Y minus y start, maybe here. No. Compile first and plot. No, maybe we need to do y plus y start. No, that looks better. Y plus my y start minus y end, maybe? Oh God. Y plus y start, so it's moving up. Minus, no, it should be, no, this might be it. Y plus y start. Is this not correct? Because here I'm saying I want to range y from minus 6 to 10. And it looks... it's something's still wrong. Of course I need to do the same for x later, but first I want to figure out the y part. Y plus y start, y minus y start, y... Y start is minus 6 in my example. Y is, for example, for the x-axis is 0, so it must be 6. over relative to the start. I have the feeling that I'm getting close. Y and no. Where's this drawing software here? Draw. This is not a coordinate system. No, it's not. This is the coordinate system. This is the display X and this is the display Y. I want to draw something here. So I have to offset by the screen width divided by 2 plus additionally some tiny bit here, this fraction here. This needs to be Y. No, in this case X. X, oh god, and minus X start divided by the scale, maybe? No, multiplied by the scale. Multiplied by scale. Yeah, but didn't I try that already? No, that's wrong, because the scale is this. If I just add... No, this would all cancel out and just add the width. Basically, the question is, oh, this is such stupid elementary school level mathematics, and I'm spending so much time here. The question is, no, I don't want to open an image. Let's create a new Canva here. If we have an arrow of numbers starting somewhere and ending somewhere, what's the center? Is it 0? If it's not 0, what is it? It's just an average calculation. Why? Need to fix up my command to compile and execute right after each other so I don't forget the compiling all the time. So now I'm compiling here and executing. Okay. Oh, this is wrong. Y end minus y start divided by 2 multiplied by the scale. Maybe it should be plus. No. Y end minus y start divided by 2 gives us the center point. For example, no, it does not give us the center point, because if y end is 10 and y start is minus 10, then I would expect the center point 0. But if we divide by 2, then it's 10, because y end is 10, minus 10 is 20, divided by 2 is 10 again. Huh? Do I have to do plus here? How do I get the center point between two numbers? I would expect that the average works. But if we do y end is 10 and y start is minus 10, then the average doesn't work. Why doesn't it work? Y end is 10, y start is minus 10, divided by 2. That's still 10, because y end minus, in case we do minus, I mean. But averages are, of course, plus. Of course. Oh, then this should work, shouldn't it? Error. There's somewhere a missing semicolon. Where is it? Plot C, line 111. No. Expected. Wait, I messed something up. Line 34. It's just a parenthesis. Okay. And that's it, guys. That's it. I just... Holy crap. I feel like I'm going crazy. No, really, had I paid attention in elementary school, I would have saved, I don't know how much time in this episode. This just shows how important elementary school is. I don't want to. Yeah, why? How am I even supposed to show you anything interesting in computer science if I cannot compute averages? Okay, but let's do a final demonstration. I hope this time it works. But if it works, it's really a powerful, it's a super powerful application. Yeah. So we've done a lot of stuff. We've done graphics programming in this episode. Before I talk so much, let's just see if it works. And it works, but let's just improve the function a bit to make it more interesting to look at. Right, the scale should maybe be something like sinus, and then let's make a higher frequency and a lower amplitude, or maybe even here something like 1 divided by 2 and then squared. No, 0. No, that's fine. Let's not overcomplicate it. Sine x, and then let's lower the amplitude by multiplying with 0. Oh, damn it. By multiplying with 0.2. Okay. Yeah. So it seems like our function plotter is working. That's awesome. We are really able to plot any function now. Let's lower the amplitude, edit the frequency again to, let's say 3. That's roughly pi. We can now plot any function that we want. That's sine x multiplied by, that's essentially sine x multiplied by x squared, but we could also do square root of x. And then let's see what that does. Okay, that's the result. Of course, square root is not defined for negative numbers, so conveniently it's not plotting those for us. Then let's do something like logarithm of x, or square root of, yeah, of course that's not defined either. I think sine x multiplied by x maybe. Yeah. And then let's increase the amplitude again a bit. Something like this. And let's change the axis a bit to make them more symmetric, from -6 to 6 on the y-axis. And this is our arbitrary function plotter, guys. This was an awesome episode because we learned just, I know it took a while, but just recall how many different programming concepts we touched. We did graphical user interface programming. We did mathematics, or at least mathematic function expression parsing. So we can now input any function into this and get it plotted. Any function that you want. That's awesome. So we can do generic parsing of mathematic functions now. We can do graphical user interface programming, and we've even done geometric transformations to be able to plot any range of x values and any range of y values, and at any step size, at any precision that we want. So there's basic programming, graphical user interface programming, there's parsing, and then there's geometric transformations, which is there's so many interesting things that we did today. Let's not talk too much and close this episode. I hope you enjoyed it. I know it took a while, but please leave a like. And next time it will be shorter, maybe. Let's see. Depends on whether I learn my my elementary school calculations or not. Okay, see you next time. Bye bye.